Hello, sir.
Yes.
Is the week 4 is also there for in the syllabus for the quiz one?
Yeah, week 4 is also
Yeah.
there.
Okay, sir.
This Friday week 4 is going to release, so we will having the syllabus from week 1 to week 4. Okay, so let me share my screen now. Is the screen visible?
No, sir.
Here it is visible
Yes, sir.
now.
No.
It's visible or not?
Yes, sir, it is visible.
Visible, sir.
Can you see in the full screen? Are you able to see the full screen now?
No, sir. Only
No, no.
PowerPoint slide is.
Okay, so let me share my full screen. Then I think that will be. Yeah, for discussion of the questions we will be having on the Saturday session. We can discuss activity practice or even previous week's questions in Saturday session. So this session is already only for the summary for week 3, and if we get the time after that, we can have questions as well. No issues.
Okay, sir.
Okay, so okay, so now can you see the screen, the full screen?
Yes, sir.
Okay, so let us start now. So as we are in week 3 now, and week 3 is all about the clustering, the new algorithm. So before we start, so let's see what we have done till now. So in you have seen week 1 and week 2 we have done PCA, and we have extended this notion of PCA to the current PCA, right? And so what PCA does? PCA actually used for dimensionality reduction. It's a dimensionality reduction technique, right? It's very standard technique in machine learning, and it's very powerful, very handy. If you see lots of machine learning models, you will find this techniques very useful, because it's actually transformed the original feature space into some another feature space where we can represent our set data set better, in a better way, right? And it actually reduce the dimension of the data set, and the dimensions that we get after applying PCA is different. Those dimensions are different from the original dimensions, right? And actually we tries to find those dimensions where data set can have more information about the distribution of data set, right? And we just try to throw out those directions which contains the less information about the data set, and or just say we also we try to find those dimensions which has the highest variance of the data set, and we just throw away those directions which has the least variance of the data set. So for that we have very powerful technique, which is principal component analysis, and those principal components becomes your new dimensions, new features, right? And if you will work in real world data set where you will encounter with lots of features, let's say 100 features or thousands, even more of hundreds features, right? And there you never knows which of those features are redundant and which are which contains the most information about the data set. So for finding those features which are redundant that you don't want to use for further analysis or any modeling, ML modeler, you want to throw those features, and the PCS does that task for you, right? And we have we have already seen this algorithm, which is called principal component analysis in week 1, right? And we have extended this notion to the kernel PCAs, where we see that the PCAs all allows demands the data set to be to live in a linear subspace of some higher dimensional space. But if it is not the case where the data set is not lives in the linear subspace, then we transform our data set into higher dimension, and then we apply the kernel PCA there. Okay, so these two notions we have seen in big 1 and big 2, where we try to represent our data set in a better way, in a better dimensions, right? Now we are moving to the next, which is again a very powerful algorithm in machine learning. It comes under the clustering methods. So what is clustering? So how many of you have gone through week 3? It would be better if you already have gone through week 3. If not, again, it's not very hard. Week 3 is gonna be easy part. Okay, so clustering, as the name suggests, clustering is the partitioning the data set into different parts, different groups or different clusters. So it's the partitions of data set into different groups. Right? And it's again a unsupervised learning algorithm. It means that the data set doesn't have label associated with itself. Okay, so again, PC was a unsupervised learning algorithm, and this one again a unsupervised learning algorithm. Okay, so our task is to, you have been given data, the same notion we are following, X, where X of Z, B cross N. Actually, we are not working with the data matrix now, but you have these notions always. If we are taking different notions, then we will explicitly mention that. But for now, you assume that X has a data set, and where X you have n data points, x1 to xn, and you want to group them into into different groups. Or say you want to partition the data set into different clusters, right? Likewise, you have seen some. You have been given image, and you've been asked to find. You have been asked to group uh, groups of humans or group of trees. Then what you will do? You will just look at the picture, and you will try to find out the similar kind of features which look like human and which look like trees and all, and then you will group them into two different clusters. So same kind of problem task we have to do now with some different data set. Okay, so we are assuming there are n data points in the data set, and now we have to cluster into different groups. Okay, so our goal is that we have been given data, and we now to partition the data set into k different partitions. So k here, let's assume for now it's known quantity, and in the later section of this session we will see for a given data set what will be the what will be the best value for k, and how to choose the value of k. But for now, it's assumed that k is known to you and it's a fixed quantity. Okay. Now, so how many such partitions you can make if you have been given n data points and you have to partition into k different partitions? Then how many configuration are possible? How many such partitions you can form? So as you know, each and every data point can go into out of these k boxes, k groups, right? These are k groups, and each and every data points go in any of these boxes, right, or any of these groups. So how x1 has how many possibilities? K possibilities. Similarly, all these endpoints have k possibilities to go into, right? So total number of partitions that you can form if you have to partition n data points into k groups, which will be equal to k raised to power n, right? So yes, these many configurations are possible, but are to choose which out of these total k raised to power n possible partitions, which one
Sorry
is the
to
best
interrupt, sir.
partitions that we are looking for?
It should
Yes,
be
sir.
n to the power k, right? Because there are n data set, and it have k possibilities to go.
So first
Okay,
data point
first.
has k possibilities, right? Another one again has second data point again has k possibilities.
Oh, okay,
Similarly, the
okay,
ns
okay,
data
okay.
point has k
I thought
possibilities.
I thought in inverse method. Sorry for that.
Okay. So now your task is to find the best configuration, right? Best partition. So what I mean by best partition, we need to define, we need to quantify those partitions, right? We need to define which one is the best. So how to define the goodness of a partition? We need a metric to quantify the goodness of partitions. Okay, so we will see how to define the goodness of a partition, but for now assume you have to find out of these total partitions, you have to find which one gives you the better result or better partitions. Okay, for that we have a very popular algorithm in machine learning which is called Lloyd algorithm, and most common name for this algorithm is called k-means algorithm. You mostly find this name for this algorithm. And here I'm going to describe the very informal way how the algorithm works, and then we'll go to the more formal ways to define this algorithm. Okay, so what happens in this algorithm? Let's see. Then we'll try to understand the idea behind this. Okay, so now for assume we have been given data set. It means you have been given n data points, and now you have to find, this is capital K. This is capital K clusters. Now, so you have to partition the data set into K clusters. Okay, so this K value is again known. We haven't find which value of K is better for your data set, but for assume now K you already know. Okay, so the algorithm says that first you have to select K different clusters means randomly. It means that if you have to find, let's assume K equal to 3, you have been given and n data points is given to you. Okay, now, so what you will do, you randomly assign 3 data points as 3 clusters means, or generally it is called centered as well, or clusters means. Okay, then what you will do, you will choose each and every data point. You will find the distance of that point from the clusters means. Let's assume you have been given this data points. This is your data set. This has been given your data set where you have to find, let's assume you have to find 3 clusters in this data set. Okay, so this is your distribution of the data set. Now what is your first step? You will randomly choose 3 data points as a cluster means. So randomly means it can be uniformly out of these n data points, you can choose any 3 data points randomly. Okay, so let's assume you have been chosen these 3 data points as a cluster mean, these 3. So you have chosen this uniformly or randomly. So this, let's call this these data points as mu1. The first central mean, second central cluster mean, and the third cluster mean. So what is the next step? You will pick every data points, and actually you have to assign each data point into one of these clusters. Okay, so what you will do for assigning the data point into the clusters, you will pick any data point. You just find the distance of data point from all these clusters and choose which is the minimum distance. Let's say assume I'm to find which clusters this data point belongs to. So what I will do, I will just find the distance of this point from these 3 clusters mean, and I come to know that this one is the minimum distance. Okay, so let's call this is the minimum distance. So I will assign this data points to this cluster 3. Okay, so this data point goes to cluster 3. Similarly, I will pick this point. I will find the distance from all these clusters means, and pick the minimum distance. So if this is the minimum distance, then I will assign this data point to the cluster 1 because this is at the minimum distance from cluster mean first. Okay. Similarly, I will pick each and every data point. I will find the distance from 3 clusters means, and then will assign the respective clusters into the respective clusters. Okay.
Sir, can you explain the step 2 again? First of all, we randomly choose some centroid. After that, we will calculate mean to each and every centroid.
No. So first we have chosen these three as the centroid or this cluster mean, right? Randomly we have assigned these 3 data points and the as a centroid. Now what we have to
M1,
do, we
M2,
have
M3 we choose randomly.
randomly,
Then,
completely randomly, this uniformly out of these n data points.
okay. Then,
Okay. Now what you have to do, you have to assign each data point into clusters 1, cluster 2, cluster 3. Okay, you have to find 3 clusters, right? K is given to you 3. Now you have to find 3 clusters. So what you have to do, you have to assign each and every data points to one of these clusters. To assign the data point into the cluster, what you will do, you will find the distance. The distance can be most probably Euclidean distance you are using here, but it may be some other distance as well. But most probably this distance is used, Euclidean distance. So what you will do, you just find the distance of that data point from all given 3 clusters. Clusters means, and you will choose the minimum clusters distance, right? So let's assume this data point you have to assign one of these 3 clusters. So what you will do, you will find the distance from this point, and this point, because these are your clusters means. And you come to know that this is my minimum distance. So you will assign this data point to cluster 2 because it comes in, it is at the minimum distance from mu2.
Okay.
Is that clear?
Okay, sir.
Okay. Once you do for each and every data points, you have 3 clusters. So maybe these data points have come to these data points have come to cluster 1. These data points has come to clusters 2, right? And these data points have come to cluster 3. Now you have 3 clusters. These all data points come to cluster 1. This data point goes to cluster 2. This data point goes to cluster 3. Now, what is the next step? So the next step, what you will do again, you will find a cluster mean because you randomly chosen this cluster mean. Now you will reassign your cluster mean. So reassigning the cluster mean, what you will do, you just find the means of those data points. So this is your cluster 1, this is your cluster 2, this is your cluster 3. Now your cluster mean for cluster 1 will be the mean of these data points. Let's say you have 20 data points here. You will find the mean of 20 data points, and the mean now will shifted somewhere here. Okay, this is now new mu1, new central. Okay, similarly you will find the mean of these data points, and will find that mean will be your new mu2. So let's assume now this is become the new mu2. Similarly, you will find the mean of these data points, and let's assume your mean has shifted to mu3 here. So now you will work with these.
Sir, this mean the green dots, the mean, that means all the data point we have to calculate the distance from centered 1, centered 2 and 3, and after that make it average.
Yeah. So when you have founded these data points belongs to cluster 1, all these data points belongs to cluster 1, you will find the mean of these cluster points.
Okay.
That will become your new mean, new cluster mean. Okay. Similarly for the second cluster. So you have come to know that these data points belongs to cluster 2. Okay. So you will find the mean of these cluster points, and that will become your new mu2, new cluster mean second. Okay. Similarly for the cluster 3, you will find the mean of cluster points that belongs to cluster 3, and that will become your new mu3. Okay. Now you will repeat the step 2 and 3 until convergence. Okay, so what I mean by convergence, when this cluster mean does not change, right? Or say the reassignment of the point doesn't happen. Now again you will find the distance of this point, you will make the new cluster. So if again you will find the point distance of this point from the cluster mu1 and mu2 and mu3, you will find that this point is at least distant from mu2. Then now this point has reassigned to cluster 2. Before it was in cluster 1. Now you have found that this cluster is at the maximum distance. It has. Okay. So now you have found that this data points now at the minimum distance from mu2 rather than mu1. So you will reassign this data points to the cluster 2. So you will repeat the step 2 until convergence. Convergence means you keep on repeating these steps till there is no reassignment of the data points or there's no change in the cluster mean. Right? So this is called K-means algorithm. Is okay. So is this algorithm clear? What actually happening here?
Yes, sir.
Okay.
Oh, one more thing, sir.
And sir, when it is happened,
Sorry.
when convergence happened in the data set?
When it may take some number of iterations. It may be larger iterations, lesser iterations, depending upon your initialization.
And sir, if after two consecutive iteration, the assignments have been same, like the
No. So yeah, we will talk about this. If the reassignments happen, then your partitions or say your clusters will not repeat itself. Okay, so reassignment happens. It ensures that your partitions are not repeating from the previous partitions.
And if reassignment is not happening for
Then
two iterations.
you say that the algorithm has converged.
Okay. If it is not reassigning, then we can directly say that it
Yeah.
has been
So
converged.
those will become your final clusters.
Okay.
Sir,
Sir, one question.
sir, is it possible that you plot some 10 or 12 data points in the graph and then
Okay.
use this
Okay.
algorithm?
So let's do this again for some. Okay. So let's take some data points like this.
If very less.
Okay, so these I'm taking 10 data points. Okay, now I am to find clusters within these data points, and two clusters I am to find k equal to 2 I am taking. Okay, now what will be your first step?
Two centroid. Choose two random centroid.
Randomly you will choose two centroids. Randomly means all these 10 points have equal probability of getting selected as a centroid, right? So all of these data points have a probability of 1 by 10 being selected as the first mean, right? Central means, or say cluster mean. Okay, so let's assume those data points have been selected like this. So your first cluster has selected this one, mu1, and this one has been selected mu2. This can be anything. This can be this one, this can be this thing, or anything, right? Assume you have been selected mu1 this one and mu2 as this one, right? What is your next step? You will find the clusters respective to, you will find those clusters, cluster 1, cluster 2. Okay, so you have to find which data points goes to which cluster, right? So for finding those, what you will do?
Calculate Euclidean distance of every data point to centroid and
You
make
will
two
check
clusters.
which is the minimum, right? So for this
Yes.
data point, you will check this distance and this distance. So which is minimum? Mu1 distance. So this goes to cluster 1, right? And similarly, let's say this distance is minimum. This goes to cluster 2. This goes to cluster 2. Similarly, this will go to cluster 2. This goes to cluster 2. This goes to cluster 2, and this goes to cluster 1. This goes to cluster 1. So now this is your cluster 1, and this is your cluster 2. Okay, so it's a hand coded, so assume that this distance is more than this distance is less than this distance. Okay, for now assume this it's hand coded. You can find that this distance is similar, but assume this distance is less than this distance, then you have found this clusters and this cluster, two clusters, right?
Yes, sir.
Okay, now what is your next task?
Excuse me, sir.
Yes,
So what if the distance is same for both the centroid?
same, then you randomly assign one of those clusters, C1 or C2. Let's say if this data points has the same distance from mu1 and mu2, then randomly you just take one of these, C1 or C2. It's a try-waking case. In try-waker, you just randomly assign in one of those clusters. Okay, so what will be your next step now?
Calculate mean centroid of
Now
every
you will find the new means. Okay, so how you will find the new mean? You will take all the data points from cluster 1 and then find the mean. Let's say these data points belongs to cluster 1, then you will find the mean of this. Let's say mean is coming out somewhere here, right? Now this will become your mu1, and similarly for this data point, these will become
how you plot the new mean? This is my question.
these are some data points, right? You already
Yes.
know these data points.
4 data points are inside cluster 1.
Cluster 1. You will find the mean of those clusters point.
Mean means centroid to previous
Means
centroid to
if x1, x2, x3 are the points here in C1, then you just take x1 plus x2 plus x3 plus
okay.
x4 by 4. This is
And
your mean.
It might not be a point on the data set.
It might not be the point from the data set. It can be anywhere.
x as well as y distance also if it is a two-dimensional plane.
Yeah. If two-dimensional, then the data point something like that. 1, 1 plus 2, 2 plus 3, 3. plus 4
Then
comma
we will
4.
calculate mean of x distance as well as y distance.
Of course, that's how you will find the distance of two-dimensional data points, right?
Okay, okay, okay.
Okay, so it will become 3, 3, 6, and 4, 10 by 4, and 10 by 4. So this will become your new points data, new mean. Okay. Similarly, for d-dimensional points, you will have 1, comma 1, comma 1, comma 1, d dimensions plus 2, comma 2, comma 2. Similarly, you element wise do the mean, right? Is that clear?
Hello.
Yes,
Yes.
sir, clear.
So, but the means may not necessarily be one of the points, right?
Yeah, need not to be one of the
So,
points.
in which case we take the shortest distance?
Yeah, of course, we take the shortest distance.
Okay.
Okay.
So, but so in the real world practical examples, usually the means are not lying on the points.
Yeah, mean doesn't lie on the points. So in this case, you can see that this mu1
Yes, sir.
may somewhere lie here, right?
Yes,
And
yes,
mu2
sir.
may lie somewhere else. So
Yes, sir.
this is not any of these given data points.
Yes, sir.
Now, so now your new mean, this is mu1, this is mu2, right? Now what you will do, you will again reassign your data points.
Yes, sir.
Okay, so again you will do the procedure. You will pick this point, you find the distance from here. You will see this is the minimum, so it goes to C1. Again, you will find the distance of this goes to C1, this goes to C1. Let's say this point, let's assume this is lesser than this one. Now this point have been reassigned to this mu1, okay, C1 rather than mu2. Let's say this is the minimum distance from mu1, okay. And similarly, let's say
How we will decide that optimum minimum distance? Which one is optimum minimum distance?
No. You will take the minimum one. So you will find the best distance of this point from here and here, right? Two distances,
Okay,
which is
okay.
the
So
minimum.
check every data point to mu1 and mu2.
And mu2.
Okay.
Okay. So let's assume these 5 data points have come to this cluster 1 now. Okay, so this will become your cluster 1, this will become your cluster 2. So this become cluster 1, this will become your cluster 2. Similarly, you will find the new mean. Let's assume this has come here mu1. So this will become your new mu1, this will become your new mu2. Okay, and let's assume you will do the again repetitions and you find that there's no reassignment of the data points, then these will become your final clusters. Right? That's the idea of convergence. Is the idea of convergence clear?
Yes, sir, clear.
Okay. So this is how a k-means algorithm works.
Sir, I have one question here. Can you help us understand how can we interpret the convergence from the perspective of a local minimum and global minimum?
Local minimum, global minimum means what?
In general, like, for example, like, global minimum is the one solution. For example, if you have a parabola kind of a solution, the global minimum will be the bottom point actually. That is where the optimal loss will happen, right? Like the least loss will happen in
So
general.
here we haven't defined the loss, right?
We haven't, sir, actually.
Yeah. So we'll come to that part. We will decide that metric.
Okay, sir.
Okay. So I can see some of you trying to join the meeting. Let me check. Okay. So till this point, any doubt?
Sir, in real life scenario, it may happen that number of features is greater than number of observations.
Yeah, it may happen.
Okay. That's why we have to calculate X transpose. That means K matrix.
That is for
Sir,
PCA you are talking about. Here we haven't
Yeah,
found XX transpose something like that.
yeah,
Right?
exactly. Oh, yeah.
Okay.
sir,
So
excuse me, sir.
yes.
Sir, I have a doubt with the k-means algorithm only, but sir, it's related with the programming question. So in the last question for programming, which you have to recalculate the new centroids. So once you find the mean of the clusters, and if the means are not lying, is not one of the points in the cluster, So then the new centroids would be what?
No. So you are saying that you are founding the mean of the new clusters,
Yes, sir.
and the mean
Yes.
is lying outside the cluster.
So yes, the mean is not one of the points in the cluster.
Yes, so it may happen that will work as your new cluster mean.
Yes,
And
but then what is the new centroid?
That cluster mean is again your new centroid. It's just the another word for calling cluster mean as a centroid.
So, but then the centroid is not in the data set.
Yeah, it can happen. In most of the
Okay.
cases, it will be the case that the
Okay,
centroid will not be the data point.
All right. Okay. Thank you, sir. Thank you. That was my confusion.
Okay.
Sir, also in the lecture, there is one statement was given actually. The converged solution may not be optimal.
Yeah. We'll come to that part.
Okay, sir.
We'll come to that part, right?
Okay.
So this is just informal base how the algorithm works. Now let's move to the defining in more formal base. Okay, so we're using some notations here. That notation you may find some confusing. If you find those confusing, please stop me and ask me, because these notations we are going to use throughout the lecture. Okay. So similarly, we have n data points, and now for every data point, we are defining a function with cluster indicators. And here the subscript or superscript denotes the tth iterations, right? We'll come to that. So this Z1 denotes where the x1 data points goes. It maps it is a function. Actually, it maps the cluster index. I mean the ith data points to the tth the cluster index to the ith data point. It means that, so if Z1 takes the value 3, it means that the X1 goes to cluster 3. If Z2 takes value 1, it means that the second data point goes to cluster 1. Similarly, if Zn equal to 5, it means that the nth data point goes to cluster 5. Right? So is this clusters indicators clear what they mean? This is just notations of the defining where the ith data point going. So we are calling it as a Zi. So Zi means that where the ith data point going. This cluster the ith data point is going. Okay. Similarly, we have n such indicators. Okay, and T here denotes the tth iteration, because remember in every iterations your data point may belong to different clusters. It may reassign to some different cluster. So in tth iterations where ith data point is going, it is denoted by Zi. Okay, so this is the notion we are following. Now, so your initialization will be some random points, right? So it means that, so this denotes the clusters where x1 goes. This denotes the cluster index where the second data point goes. This denotes the clusters where the nth data point goes in the 0th iteration, right? So this is your initializations. Now we are following the same steps, right? But in the more formal ways. So remember these steps, right? Just find the initialization, then assign the data points into the clusters, and then reassign the cluster means, and then reassign the data points, and keep on doing until convergence. So these steps we are following, but in the more formal ways now. Okay, it's nothing new.
One question, sir.
Yeah.
Can you go to the previous slide? Yes, sir. Here the ZTI in the slides, professor said that it belongs to 1, 2, dot to K, like
Up to
the
K.
number of.
So here I left it blank. It means that I want to ask you where what can be the possible values for ZIT?
A number of partitions.
Yeah.
Like,
So it denotes where the ith data point going. So it can be from one data point to k data points, right? Because you have total k clusters. So this will go from 1 to k, right? So ith data point can go in any of these k clusters.
oh, means if it is 2, then
Then
like,
it means that ith data point is going to cluster 2.
okay, and two Z, like ZT1 and ZTN can be 2, right?
Sorry, Z.
ZT1 and ZTN.
Yeah, it can be one. For any data points, it can be same, because in a given cluster there may be more than one data points, right? So it means that if it is k, it is k. It means that the first data point and another data point are going to cluster k.
Okay, got it.
Okay. So this is your first step. Here you have to randomly initialize your centroids. So these have become your centroids.
Lloyd algorithm are same. Then why it is written differently?
No, it's just a different name for Lloyd algorithm. It is K means. it's just different name of Floyd algorithm. Okay, so what was your second step? You will find the mean cluster. You will assign the clusters, right? So until convergence, you will keep on doing this. You will compute the means of the k clusters. So what you will do, you will take all those points which belongs to cluster 1. So this indicator makes sure that you will take only those data points where which belongs to cluster k, right? So here what we are doing in the kth iteration, we are finding the mean for the kth cluster. So this is the mean of kth cluster. So what will be the mean of kth cluster? You will check which data point belongs to kth clusters and just take the mean of over those data points. So what you so this indicator function makes sure that it is 0 when it is not k. It means that it will banish that data points which is not belonging to cluster k, and it will keep only those data points where this is true. It means that it will take only those data points which belongs to cluster k, right? And just the summation over those and total data points in that cluster. So this will be the mean of the kth clusters, right? That's what we do. We just take the data points into kth cluster, we'll find the cluster mean, and that will be your new clusters mean, new clusters, right? Cluster mean. Okay, so actually this one, your Z10 was your so this is your initializations. I mean, you can randomly choose any of these data points and you just initialize your data rather than data point assigning data points randomly. What you do, you assign random some k clusters. So you will assign data points as mu10. So you randomly assign some means. Okay, mu10, mu20. You randomly assign those means, k means randomly. Okay, so this should be your initialization. Okay, once you have completed mean, you again do the reassignment. So how to do reassignment? So assume that the ith data point goes some one of these clusters mean, right? So it can be any of these key clusters. So in the t plus iteration where it will go, you will find the distance from all the clusters, right? So this will give you for all k, you this will be the clusters means of all the kth clusters in the tth iteration. You will find the distance of xi point to all the centroid cluster means, and you will check which is the minimum, and you will just report that k. So that will be your reassignment of the data points, right? So is these steps clear?
Sir, can you explain this last term, the u power t then k, how they are actually related? I mean, how to calculate this thing?
This last step, right?
Yes, sir. This last actually. I'm
Okay,
very confused
so
about this notation u ki power t then k, right?
okay,
This one
yeah.
actually.
So what does this ZIT mean?
This is I is a data point, right? Data. I mean data. Right?
Yeah. So it is the cluster where I data point going in the
T is
tth
a
iteration,
address.
right?
Okay.
Yeah. So in the t plus iterations where this ith data point going is denoted by this, right?
Yes, but sir, the reassignment left side, right? You've taken z base I. So don't you think it should be I, sir? I mean, that's what I'm confused, sir.
This one.
Yeah, yes, xi minus u ki power t, right?
Yeah,
Power
this
t
thing.
base k.
Okay,
Yes, sir.
so I'm saying that it means that the clusters where xi point going in the tth iteration, and this denotes the cluster where xi data point is going in t plus 1 iteration, the next iteration.
Okay.
Okay.
T plus
So
1.
how you will find the next cluster for this xi data point? What is the way for finding the next cluster for this data point?
Not sure, sir.
You will find the distance of xi data point from the given means, center cluster means.
Okay.
Okay, so in the tth iterations, you have mu1 t, mu2 t, up to mu k t, k, total k clusters, right?
Okay.
In the tth iteration, these are your central,
Okay.
centroids. Now you will find the distance of this xi data point from all these k centroids. That's what it is doing. It is finding the distance. Here, distance is Euclidean distance, or this L2 norm, Euclidean distance. Okay, so it's finding the distance of xi data points to all those k cluster means, and we're checking for which k it is minimum. It means that it will report that k for which the data point is at least distance.
Okay. Understood, sir. Thank you.
Understood?
Sir, it is calculating k also.
It's finding that k.
K for
It's
the
finding that cluster. I mean, you mean to say it's finding that cluster from which the distance is minimum,
Minimum, yes.
right? So K will keep on varying. We'll keep on checking with each and every cluster.
Yes, for
And
every
yeah,
k you will find this. This k will vary. So this is a small k. K is varying from 1 to capital K.
yeah, okay.
Okay. So for every centroid, you will find the distance and will report that k for which it is the at a minimum distance. The xi data points.
K,
Right?
K is fixed, means 1 to K it will vary one by one.
Yeah. That capital K is fixed. That we haven't talked about, but just for now, assume that you already know how many clusters you have to find into the data set. Okay.
Okay.
So this is the same algorithm that we have discussed, but in a more formal way that we have followed in the lecture. Okay. So is this clear? This steps clear? We are doing nothing. We are just initializing your means, then assigning data points depending upon the distances. You keep on doing. You will again assigning each and data points into the cluster, then finding the clusters means, then again doing the reassignment of the data points. Similarly, we have done before, right? Okay. If done, let's move to the next part. Okay, so we are randomly initializing your clusters means. So will the initialization affect your final clusters? That someone has asked me that what the optimal solutions means, right? That the clusters may not be optimal. Okay, so there now we discussed that. So let's assume here. So the same example I will take. Okay, so let's take that example again. So you have these let's say 12 data points here. Okay, now you have initialized you have to find two clusters. Let's say k equal to 2, capital K equal to 2. So you have to find k cluster. So algorithm says you just randomly initialize your data points. Okay, so for the very first initialization, I've chosen this one. I've chosen I've chosen this as the mu1, and okay, so I've chosen this as the mu1 and this is as the mu2. This is the initialization. Okay, in the second chance, I've chosen the same data set I'm taking. Okay, and I've changed my initialization. The very
Is
first
there any
initialization.
logic that how we initialize mu1 and mu2 first
It's
time?
just random.
Because
It's just random. It's just random data points. I'm picking some two random data points. Okay, so let's say this is my first initialization and this is the second initialization. Will this end up being this two initialization will end up in two different clusters, right? Because if you see here, the this data point will go to cluster 1, right? And this data point will go to cluster 2. Okay, you will find the new mean. So mu mean will lie somewhere here. Now this will have become your new mean, mu2 and mu2. Again, you will reassign the data points. So if you see here, these 6 data points will come to this cluster C1, and these 6 data points will again go to the cluster C2, right? Second clusters. It means that there's no reassignment of the data points. So these are your final clusters. So this will become your C1. This is your C2, right? Because the algorithm has converged, because there's no reassignment of the data points. It means that the algorithm has been converged, right? So in this initializations of the means, centered means, these two are your final clusters. But now look at this initialization. In this initialization, what will be the cluster? Very first cluster. So if you look at this point, right? So this will be at a minimum distance from this mu1, right? And this distance will be larger. So this data point will go to mu1, this go to mu1, this go to mu1, this go to mu1, and all these data point will go to mu1. So this will become your the cluster 1, and this will become your cluster 2, right? Now what you will do, you will find again new mean. So if you take the mean of this somewhere here, or maybe this point again will become your mu1, and let's assume now your new mu1 has come to this point and your new mu2 has come to this point. Again, you will do the reassignment of the data points, and you will see that again the reassignment is these reassignment of, I mean, the data points are not getting reassigned. It means that these two become your final clusters, right? So so we have seen that depending upon the initialization, your clusters may be different. Here you are getting these as a cluster, here you are getting these as a cluster. So what you think will be the optimal one? So if you look at the data set is looking something like that. Some data points on this line, some data points something this line. So you may think that this one was the optimal solution. Okay, so 2 points here to note. One thing is that the initialization will affect your final clusters, right? And the second point, which one is the optimal that you have to find. So for finding that optimal, we have to decide a metric that we were talking about initially. So our objective function is you have to minimize this thing, right? So it makes sure that what is this? You have to take every data point, its mean, and then find the distance. So in this scenario, you will pick every data point, find the distance of its mean. So so objective function in this case will become, you will find the mean distance here, distance here, distance here, this distance, this distance, this distance, and similarly for this you will find this distance here, and will sum over those distances. Similarly for this objective function will become, you will find this distance, the final clusters I am taking, right? This distance, these distance, and this will become your objective function in this case, sum of those distances. So the minimum one you will pick as a the optimal solution. Okay. So what it minimum distance ensures? It ensures that the clusters are very the minimum distance gives the idea that the clusters are cohesive in nature, right? So if they are the objective function is minimum in this case, it means that the clusters data points are not far away to each other. Wherever if the objective function takes larger value here, it means that the clusters data point are distributed far from each other. So we want to make sure that within the cluster data point are not far away. It means that we want to minimize that objective function, right? So that's how we define the objective function in the k-means. So this becomes your objective function, and here you have to minimize this objective function, right? So those two things, the initialization will always affect your final cluster. Second, which one will give the optimal, which you will pick as a optimal solution, the one which gives the minimum optimal objective function value.
Sir, one question here. With respect to this loss function or the minimization function, yeah, I mean, the objective is to find out the clusters which minimize this function, and that is the global minimum, correct? I'm just thinking, when can we arrive at a local minimum? Like, is there any possibility of arriving? Like, just thought of understanding from that perspective.
Okay, so here what will happen if you try to draw the loss function and check the local minima? So it's like you are finding a vector. Let's assume you have only you have two clusters, C1 and C2,
Okay.
right?
Okay.
Now some data point belongs to this cluster, some data point belongs to this
Right.
clusters, right? And you are finding the distance of every data point from the cluster mean. Let's say mu1 is the cluster mean, mu2 is the cluster mean. Okay. Now you are choosing those means, those clusters means those vectors. Let's say v1 and v2. You are choosing those vectors. When finding the distance of each data point, that distance becomes minimum, right? That will be your local minimum or global minimum, right? In this case, it is if it is a convex function, your global minima become local minima, right? So all the local minimum it become global minima. So I am finding that vector, that mean, for which if I find the distance of each and every data point from that vector, that distance should be minimum, right? Or say we are finding what? We are finding xi minus b, that vector for which this is minimum. So if you solve this optimization problem, that you will find that actually this b vector is nothing but that centroid, that centered cluster mean. So this b is nothing but x1 up to x l upon f. Okay. Or simply you just say, if you have been given 4 points, you have to pick that point. If you you have to pick that point when finding the distance of all these data points from that point. It should be that sum of that distance should be minimum. Let's say you have this b1 and this is your b2, this is your b3. From finding the distance, sum of the distance of from these data points, this will give the minimum distance. Probably this one, right? So out of all those data points, the mean is the one which gives the minimum distance, sum of the distance. Okay.
Excuse
So
me, sir.
this fact I'm gonna use in the later section as well. But for if you want to find a local minima, just think you have to find those clusters. Cluster thing which gives the minimum distances. Then find the distance of each data point from that clusters. That point. Yeah.
Sir,
Yes.
so like in this example, if the data is arranged in such a way that in both the cases we will get the same minimum distance, like then which will be the optimal one?
Okay, so it is very unlikely case where you will get the two participants which are giving the same objective function. That is very unlikely case. But even if it happens, then in machine learning algorithm, tie breaking always randomly picked, right?
No, sir,
Everywhere.
like can't we do like in a such a way like the way like the C1 and C2, how much they are apart from each other, these two cluster, and the maximum distance between them we should
Yeah. That is
use.
also a a way to evaluate your clusters, how good your clusters are. So that is method is called Silhout method. So we'll see in later part, but it's not covered in the lecture. So I won't go in much detail of this Silhout. This is called Silhout
So
score.
what's the spelling, sir?
SILHOUTE.
Okay, thank you, sir.
So you can go and check it out. It actually gives the idea of how the clusters, how good the clusters are. Okay, and it captures the intra-cluster distances and compares to the intra-cluster distances, something like that. Okay, so that you can check it out. How this course gives the idea of the betterness of your clusters. Okay, that is
Sir,
again
I
a good
have
way to
one
evaluate your
question.
clusters. Yes.
Sir, in the PCA, in the chapter PCA, we learned that all the data points we have to represent a single line and the best possible line. And in the clustering, we learn that how we
In different
classify
parts.
the data into different cluster. So my question is, first of all, if there is some data points, random data are there, first of all, we apply clustering, then then find out the best PCA for each cluster. This is the process.
For what? Process for what?
If I want to process the data points inside the cluster, then I should choose PCA. Best PCA.
No. So if you have to doing clustering, then clustering is a different algorithm than PCA. PCA is a different part. PCA is actually trying to find the different dimensions of data set, which captures the best information of the data set. Right? In the clustering, what we do, we try to partition our data set into different groups.
That I want to know. Is there any relation between clustering and PCA? Or
No relation. No, not at all.
so when I process some data points, first of all I cluster it, then PCA, where I apply PCA.
I didn't get your question.
Okay, you continue. If I raise any question, first of all I think about it, then I will ask.
Yes, yeah. So, is this question clear? Initialization will affect your cluster, right? This idea is clear. How the initialization may lead to different clusters, final clusters, right? And this is your objective function. So, any doubts till this point? Okay. So if the initialization may give rise to different clusters, and so what is the better way to initialize your clusters? There should be some better ways to initialize your cluster. Means we randomly are initializing your cluster means, right? Let's assume you have been given some data set like this, where you have been given data set like this, right? And something like this. Now you have to find two clusters within this data parts, and you have been given k equal to 2. So you have to find two clusters, and let's assume your random initialization may end up with like this, right? So in this case, you may end up with something like this. Your clusters may look something like this. but that's not the best clusters, right? So what are the better ways to initialize your data points? So think about this. Rather than randomly assigning, what I will do, I will just pick one clusters point first. Okay, so for this particular data point data set, let's take this particular data set. Let's pick one centered first. I'm randomly picking one centered here. Let's say I'm randomly pick one centered, and this is my first centered. Now for picking the second centered, what I will do, I will what should be the best central centered here? What do you think should be the best centered in this second centered should be?
Something as far as possible.
Yeah, something as far as from this point, right? So for assigning the second data point, what I will do, I will assign scores to these data points. What is those scores? If the data points is far from this point, then I will say this data point should have higher probability of getting selected as the second mean. So if this is the highest data point, this is the data point which is at the highest distance from mu1, then this data point should have highest probability of getting selected as a data point rather than selecting randomly out of these data points. Okay, so I will assign each and every data point the score, and that score is actually proportional to the distance, right? So if the highest the distance, higher the score. If the lowest the distance, the lower the score. And I will give this that as a probability distribution. And for selecting the second cluster mean, I will use that probability distribution. It means that the farthest point will have highest probability of getting selected as the second mean, and the nearest point will have the lowest probability of getting selected as the second mean, right? So this is the case for k equal to 2. That makes sense. Let's take the k equal to 3 case. Okay, so let's assume you have something like this data points. Okay, where in the data set you have 3 clusters, and you have been given task to find the 3 clusters in the data point. So you have to choose 3 clusters, right? You have to find mu1, initial mu1, mu2, mu3. Okay, so how you will choose these clusters? Randomly may give rise to the cluster that are not optimal, right? So how to initialize them in a better way? First mean you just randomly pick. Let's say you are coming out this mu1 as the random one. So mu1 you are choosing randomly. For choosing the second mean, again the same procedure. You will find the farthest point from mu1. So let's assume this is coming out to be the farthest point, and this point should be given as the highest probability of getting selected as the second mean. Okay, and it is not necessary that this will come out to be the second mean, but it should have the highest probability. Let's assume you have out of those probability distribution, and you have chosen this as the second mean, mu2. Now for choosing mu3, what you will do? What should be how you will choose second, third mean? Again, you will assign some scores to each and every data point. And how you will assign the data points? How you will assign the score for every data point? Let's say this point. Okay, so what you will do? You will find the distance from this, and you will find the distance from
M1
this.
and M2.
Sorry.
Mean of M1 and M2.
Not the mean. That can be a case as well. But what this algorithm says that you will find the distance from mu1, mu2. You will capture the minimum one. So let's say this is distance is 5. This is distance is 6. From 5 and 6. Okay. So you will capture the distance from 5. For this point, you will capture the minimum distance. So you are capturing 5 here. For this data points, again, you will find this distance, and capture the minimum. Let's say it's coming out to be 7. And out of those distances, you will pick the minimum or maximum?
Maximum
one, right? So you will find the minimum distances from the clusters, already chosen cluster point or cluster mean. Out of those minimum, for all those n data points, the point with the highest score will have the highest probability of getting selected as the next mean, right?
Sir?
Yes.
Sir, I didn't understand what value you maximized. Could you just repeat that again?
Okay, so what I'm doing now, I've chosen 2 mean, mu1 and mu2, right?
Yeah.
That idea is clear how I've chosen mu1 and mu2. mu1 just randomly, mu2 I've given some scores to these data points, and those scores are proportional to the distance from mu1. Now I'm to choose third mean, right? For selecting third mean, I will again assign each and every data point some score. Okay, and the point with the highest score, I will give that point the highest probability of getting selected.
Okay, sir.
Okay, so what are those scores? I will just find for that point. I will choose the minimum distance from the centroid as a score, because the minimum by minimum, because minimum ensures that all other cluster means are far away from that minimum clusters, right? So if it is at minimum 5, so it makes sure that the mu2 is far away from mu1 with respect to this point xi data point. Right. For this xi data point, my score will be 5. Similarly, for this data point, I will find the distance here, distance here. I will capture the minimum. Let's say minimum is coming out to be 7. For this data point, score will be 7. Right. And similarly, I will capture all the scores for every data point. And let's say you have 5 data points, and score is coming to 5 data points, and scores are coming to be 5, 3, 7, 9, or 2. Okay, so now this data point will have the highest probability of getting selected as the third mean. This data point will have the least probability of getting selected as the data point. And what are your final probabilities will become? You just make those as a probability distribution. So for making probability distribution, what you have to do? You just normalize such that they become 1. So you just add those values, and so those values will become 10, 15, 15, 24, 26. So 5 by 26, 3 by 26 will be the probabilities of getting selected as the. So you can see 9 by 26 is the highest probability. So this data point will have the highest probability of the getting selected as the third mean. Okay, now you are not selecting the third mean randomly. You have some probability distribution to select your third mean, right? And that probability distribution makes sure that your clusters are cluster means are far away from each other.
Sir, 9 is
Sir,
the
one
distance from
question.
mu1 and mu2.
Sorry?
9, the distance is
Yeah,
from
so
mu1 and mu.
this is the minimum distance of the fourth point from which is the minimum from mu1 and mu2. You will find the distance of fourth point from mu1 and mu2, and you will capture the minimum one here.
Cannot understand actually.
So what I'm doing here, let's say you have 4th data point x4. Okay, you will find that
If you take please less data point like the k-means algorithm, and then explain, then it will be better. 10, 12 data points.
less data points. Okay, I will do that.
10, 12 data points.
That calculation will become. Okay, I have an extra page here, so I can explain. So let's assume these are your clusters. Give me 1 minute. Okay, so let's assume these are your clusters. So here equal to 3. Now you have to do mu1, mu2, mu3 because 3 clusters. You find the cluster in the data set. Okay, so for assigning the very first cluster, you just randomly send 1 point. Okay, so that mu1 can be any of these. How many data points? 5, 5, 10, 12 data points. So out of 12 data points, every data point have 1 by 12 probability of being selected as the first mean. So let's assume your first mean comes out to be this one, mu1. Right? Now you have to choose second mean. So for choosing second mean, you will assign each data point, remaining data point, some score. Okay, so what is that score? So I want to make sure that that second mean should be far away from mu1, right? So if the largest is the distance, I will assign that point to be the largest score. Okay. So let's assume this point. I will find the distance from mu1. If let's say distance is coming out to be d1. Okay, and here distance to be d2. So all these distances for 11 data points, 1 to 11 data points, some distances d1, d2, dn, d11. Okay, so these are my distances. I will just make those probability distributions. So how I can make those as a probability distribution? Just to I just need to make sure that they add up to 1. So I will do d1 upon d1 plus up to d11, d2 upon d1 plus up to d11, and d11 up to d1 plus up to d11. So this will become my probability distribution. So it says that the 11 data point has this probability of getting selected as the second mean. The first data point have this probability of getting selected as the second mean, and also it ensures that the highest distance will have the highest probability of getting selected as the second mean, right? So now instead of choosing randomly second mean, I have a probability distribution to select my second mean, right? So this data point have the highest chance of getting selected as the second mean. It may be the case that you end up choosing this cluster. You are very unlucky guy, and you chosen the point which have the least probability of getting selected, and you have chosen second mean. Again, you can end up choosing this as a second mean, but this point now has the highest chance of getting selected as the second mean. Okay, let's assume now you have chosen this as the second mean, mu2. You have chosen mu1, you have chosen mu2. Now you have to choose mu3. What you will do for choosing mu3? You will again assign some data point scores to those data points. And now what are those data points? You just capture here. You have captured the distance from the mu distance from the mu1. Here you will capture the minimum distance from mu1 and mu2. Okay, so for this data points, this has been selected as the mu2. Now for this data point, you have to assign some score. So you will find the minimum distance from mu1 and mu2. So let's assume this is the minimum distance. So you will capture that. And now you have 10 data points, 1 to 10 data points. So that distance is coming out to be L1. Okay, the minimum from mu1 and mu2. Okay, and L2 is the minimum of this data point, second data points, the minimum from mu1 and mu2. So you will capture that. Similarly, you will capture L10 for all those remaining 10 data points. You will make those probability distribution. Similarly, L1 divided by L1 up to L10. Similarly, this L10 divided by L1 up to L10. Now this probability distribution you will use to select the third mean, right? And it makes sure that the largest one will have the highest chance of selecting the third mean. And this particular algorithm is called k-means plus plus algorithm. So and the other steps of the algorithm goes as the k-means, but we have a better ways to initialize your clusters means. Okay, the other part goes in the similar fashion where you assign clusters, again recompute the mean, again reassign. The same manner you go for the remaining part.
I have a question here. May I ask this?
Yes,
sorry. When you are saying we have 2 clusters, when you have 3 clusters, there is a procedure that you are mentioning, but how do I know how many clusters are there in the data?
Yeah, that we come to the next part of that, how to choose the best value of k.
Okay. Sorry to have interrupted. Please go on.
Yes. So
there is a
someone
lady
else.
who is,
Hello.
yeah.
Yes.
Hello, sir.
Yes. Please go ahead.
Sir, could you please explain like why we are taking minimum of mu1 and mu2 in the second case?
Okay, so taking minimum ensures that all the clusters are far away from that point, because I'm choosing this distance and I'm choosing this distance, right? For this particular point, I'm taking L1. So taking L1 makes sure that all other clusters mean will be far from this, right? Right?
Okay, sir, we are
Yes,
choosing
yes,
the
sir.
minimum of
Yeah.
the two, right? We are
Because
calculating both the
we-
distances.
Yeah. So we want to make sure that we want to find the clusters the far away from the already chosen clusters means, right? So if you pick the minimum, it makes sure that all the clusters will be far away from that point.
Yes, sir. Yes, sir.
Sir, why do we take the probability? Can't we just calculate the distance and choose the distance with most value?
Yeah, because now you have to select the third data point, right?
Hmm.
So third data points, I will give the highest priority of the point that is at a the highest distance. So that's for selecting that. I have some distribution. That distribution I'm converting into the priority distribution. It again says that the highest, the point which is at highest distance, which have highest probability, right? The same thing.
It is it just a convention?
Yes, it's just a convention to make sure that they become a priority distribution.
Okay.
Okay. So again, we have the same algorithm. This one, where we have initialized our data points, and all other steps goes in the same manner. But now we have the better initializations, right? Where we have chosen k different cluster mean randomly. Now, rather than choosing randomly, we have some probability distribution. We have a better way to initialize our clusters means. And why we were doing this? Because we know that different initializations may lead to different clusters, and those clusters may not be good, better cluster. So to make sure that we end up with some good clusters, we actually try to better our initializations, and this is one way to better our initialization. And this particular algorithm is called k-means plus plus algorithm. Okay, so this is called k-means plus plus algorithm. Fine.
So in this k-means plus plus algorithm, since we calculate the score specifically because of the Euclidean distance, so why is the probabilistic versus deterministic debate question comes up? So since we're calculating based on the distance, why is it a probability? And why can't we say that point D5 will be chosen as
yeah, you can do that. You can do that, but the algorithm has designed in that manner. Okay.
So because there's this question of probabilistic versus deterministic, and
that is a good point. Actually, the highest point should go as a
yes, sir.
But again, we are randomly assigning some points, right? So rather than just having equal probability, equal chances of selecting, we are giving some different distributions. Again, you can choose the highest score point as the second mean. Similarly for other points, but
okay, you can choose.
This is what k-means plus plus says.
Okay. All right. Thank you, sir.
Sir, once the probabilities are assigned, which the probability assignment is clear, then how is the choice made? Like, let's say there are 4 points. One is 1 by 2, one is 1 by 4, 1 by 4, and whatever, such that it adds up to 1. Now, how am I making the choice there? Like, how am I using the probability to choose which one?
It's again selecting a point, but now randomly selecting, we have some probability distribution. I mean that point will have the highest chances. Let's say you have 4.1, 2, 3, 4. Okay, now I am to assign second mean out of these 4 points. So rather than having equal chances will be 1 by 4, 1 by 4. Any of these 4 can be centroid, right? But rather than giving this equal chances, what I will do, I will give some different probabilities to those points. I will say this will go 1 by 4. This will go 3 by 4, 3 by 4, 3 by 4. Now 3 by 4. It will become more than 1. Something add up to 1, right? Let's say 1 by 6, 1 by 6, 1 by 6. Okay, so now this point will have the highest chance of being selected. The second mean can be any of these 4 points, but these will have the highest chance of.
Yeah, that's what I'm not able to understand. So the highest chance is this, but it may not be selected. So how is that selection happening?
Its selection is just it's like picking the ball from a box, right? Where there are 90 balls, blue balls, and 10 red balls. Okay, so there are the highest chances of selecting blue balls, right? So it's just randomly selecting, but now blue balls have highest chances.
Okay.
Again, you are again selecting out these 4 points.
The chance of selecting a blue ball is higher if there are more number of blue balls.
Yeah.
So I may increase this point that many times so that the probability gets reflected.
Yeah. So
I may multiply. So that's the process. Okay, got it.
Yeah, that is the process, right?
Got it, sir. Thank you. That was what was bothering me after the lecture.
Okay. So we are nowhere in the middle because most of the things is remain. Okay. So Now we have a better way to initialize our centroid. Now the next question that comes, how to choose the value of k. Till now we are assumed that k we already know. For a data set, this k should be the best value of best value for our data set, right? But we never know about value of k, how many partitions are present in our data set, right? In two-dimensional, one-dimensional, you can visualize your data set and can predict, but you will never encounter the data set which are have lesser dimension. In the real world data set, you will have higher dimensions, and you can never visualize how many natural clusters are present in your data set. So how to choose that particular value of k, right? So remember, our task was to minimize these things, right? If you will find you will find different clusters, you will find the distance of all the cluster from its cluster mean, and try to minimize this thing. Let's assume you have k equal to n. I mean, you have n data points and you choose n clusters. You try to find n cluster in your data point. What will be the minimum? What will be this objective value?
0.
0. Why 0? Because if you are choosing n cluster in your data point, it means that every data point has its own cluster, right? Every data point is its own cluster. It means that if you find the distance of the data point from its cluster mean, it becomes 0. So this will become 0. So our task is to minimize this thing. So k equal to n is giving me the best value of k, right? Because our objective was to minimize this, and if I choose n cluster in a data point, then our task is done because I have minimized my objective function. But this should not be the case, right? It's obvious that I don't want to find n cluster in my data point, right? So rather than having this objective function, I just want to make sure that I don't end up choosing high value of k. I have to somehow penalize this large value of k, because this objective function is always giving me k equal to n. It's saying that choose n clusters that will give me the minimum objective function value. But I don't want to do that. I just want to penalize larger values of k. So there should be some penalty function added in this objective function, right? So there are different ways for choosing k, different methods of choosing k. I'm explaining one of those methods. Okay, so there is one way, just change the objective function. Rather than having this as an objective function, I just add a penalty function here. This penalty function makes sure that whenever the k values increases, my objective function value increases, and I have to make sure that it doesn't goes very high value of k. Okay, so I just add a penalty function in that and then proceed. Okay, this is the one way that sir described, and this pk is actually function of k, and there is different way to define pk. Some of them are AIC, and I'm not sure about both the methods, but again, those are some statistical tools to find. It depends upon that likelihood that likelihood of the data set and the value of parameters, values of number of parameters in the data set, and all these. These are some statistical tools to describe this penalty function, but this is not in our course. Okay, so you just think as you have add some penalty function to make sure that your k value doesn't goes very high. Okay, there's one another method for finding k, which is called algo method. So algo method says that you just randomly start with some k. Let's say you have been given some data points and you just randomly start with some random k value. Generally, it's taken from some lesser value. Let's we start with k equal to 2. And k equal to 2, you start your algorithm, k means algorithm, and you will find final clusters. And for those final cluster, you will find the objective function value. Let's it is coming out to be f1. Okay, now you will again proceed. You will take the k equal to 3. You will find the objective function using the final clusters. Let's call it f2. Similarly, you will keep on doing for some k some values of k. Let's say I'm doing up to 2 to 5, and I'm storing my 5 values of this. So what I will do, I will draw them k against the objective value. Here objective is the sum of s squared, that norm L2 Euclidean distance xi minus mu zi. Okay, this is your objective function. Okay, so let's say put 2 equal to objective function value somewhere here. This is your f1. for k equal to
Sir, in the previous slide, can you please explain once again what is objective function? Cannot understand clearly.
Okay, I will come back to that. Let me finish this elbow method first. Okay, I will go back to that slide. Okay, so here I'm saying for different values of k, I will find the objective function and I draw them. For k equal to 2, I will choose here objective function k equal to 3 somewhere here, k equal to 4 somewhere here, k equal to 5 somewhere here. It will always be decreasing function. Remember, increasing k will always give you the lesser objective function value. And rather than choosing the least objective function value, I will choose this elbow. This k equal to 3, I will choose the best value for k. So elbow method chooses the elbow for this graph, right? So is this elbow method clear? What is happening here? This is randomly start with some value of k and keep on finding the objective function value for some different k values, and then draw the graph between k and objective function value, and just pick up this k, this elbow. The graph most likely be something like that. This, and then start going to 0. Right? For k equal to n, it will go to 0. Okay, so it will hit the x-axis where k equal to n. Right? This is your objective function value. This is your k. So you will pick the elbow
why do you
here.
choose 3? I didn't understood that.
No, that's what the elbow method says. Rather than choosing k equal to 10, because you can see that k equal to n will give me the 0 objective function value, right? So I will choose this elbow. In this graph, somewhere you will get this kind of behavior of the graph where it will start and going to 0. So that point I will choose my best value for k.
Basically, it will be like a which is initially you will see sharp drop in the objective value.
Yeah, and
after a point the drop will be smaller. That means adding more clusters is not giving you more decrease or higher decrease in basically marginal returns are lower.
Yeah,
right? So you cut off there.
Yeah. Okay. So you
Sir, can you just go back to the earlier slide where you showed the
I'm going
penalty
to
objective function? I just wanted to see it once.
Yeah. So someone also asked me to do go that, but just want to make sure that this elbow method is clear or not.
Sir, actually we have added
Sir?
penalty term in this function.
I have a doubt.
No, here I didn't add any penalty function here. I just taken that objective function xi minus mu zi all square.
Okay,
I didn't add any penalty in this method.
Sir?
Yes.
How is elbow defined exactly?
Not exactly defined. It's just the nature of the graph, where this decrement in the objective function becomes very less on increasing k. That point is actually taken as k.
So how does the model figure the elbow out? Is there any mathematical way to do that?
No. You're see sir. If I can answer that, I used this a few times. Most commercial softwares will plot this and give it to you, right? So for as k increases, it will identify the value for the objective function, and then it will plot this graph and give it to you. Then you make a choice, such a where should I cut off, because you will see a sharp drop. It will be actually sharp drop. Then after that, the drops will be very small. So essentially, it will look like your hand elbow, right? You kind of bend your hand, your elbow.
We are supposed to choose the value for.
You are supposed to, yeah.
We are at
the person
to choose the elbow. We can define.
Yes.
Okay.
Yeah.
We can do
It
that.
will just give you the graph. After that, you have to make the choice.
Okay, so it's just a visual game, right? We can do that visually.
Yes. So
it will give you
that idea of choosing how model is choosing and how you are setting it become clear when you will study about parameters and hyperparameters. So k here is a hyperparameter. Model itself doesn't learn these values. You have to set by yourself. Okay, so you have to tune these values. What are the possible values? What are the best combination? What should be the best thing? So these are user different values, and these are called hyperparameters. So you will learn about this in the future lectures.
Hello, sir.
Okay.
Sir, actually, when we do this kind of thing in PC, even we have this elbow kind of plotting for eigen values, right? So there we actually choose when the total when it is greater than 0.95. That's what we learned from the lecture. So is there anything like that that it should be above 90 percentage or like that, similar to PCA?
Not any optimal values defined as such, but there
Okay.
you say that the you pick only those directions where those captures the 95% information of the data or 95% variance of the data. You just pick
Yes,
those
sir.
values. You just lost your 5% of information. Right? There you
Okay.
find some threshold there, but here we don't define any threshold as such.
Okay. So just the drop will do. I mean,
Yeah.
irrespective
So
of whatever value it is.
yes,
I mean, whatever percentage it is. Okay, sir. Okay, thank you, sir.
Yeah. So you want me to come to this slide? What was your doubt here?
Sir, I have a doubt about PCA. Is there any game of hyperparameter tuning in PCA?
PCA. Not as such hyperparameter tuning in that's is PC is actually pre-processing part of your model ML model. So it actually doesn't require any hyperparameter tuning as such.
Can you explain what is hyperparameter tuning?
So hyperparameter tuning is different things. So you will learn it in the future lecture. So just think there are some parameters which model cannot learn by itself. You have to set those values. Like k value in the k means, right? You model itself cannot learn those values. You have to figure out which is the best value for your
Okay,
data.
sir.
So those are called hyperparameters.
Okay, sir. Thank you.
Sir, objective function.
Okay, so objective function is like you have this cluster. Let's say these your data points, and these are your second cluster. Okay, so these you have two clusters, and you have this mean mu1, cluster mean first, cluster mean second. Now, what will be your objective function? You just find the distance of every data point from its clusters mean. Okay, so you will find the clusters mean distance, these distances, and for this clusters again, you will find the distance of each and every data point from its own cluster mean, right? And you will just add all those values. So it's like xi minus mu zi. Right, so Jedi make sure that it's the cluster mean corresponding to xi and take the distance, this distance, given distance.
Sir, what is mu Jedi? Can you please explain?
Mu Jedi actually Jedi make sure that it's the clusters mean corresponding to the xi data point. So for x1 it becomes the cluster mean for cluster mean of the cluster one, not cluster one, the where the xi data point belongs.
Distance from cluster mean to data point.
Data point. It's on cluster mean. So if you are finding distance of x1, then you will find the distance of x1 from its own cluster mean. Let's say x1 belongs to cluster 2, so you will find the distance of x1 to mu2. So in this case, z1 is equal to 2, right? So z1 says that where the first data point goes, it goes into second cluster. So you will find the distance of x1 data point from the second mu2.
Sir?
Yes.
In the real world data, when we are processing for clustering with the whole process, what you have explained. So suppose the cluster came out is a 6.
Okay.
And then when we go for reversing, so maybe for some further processing of the model and something, then just to find the cluster again with the unknown data, then it may so happen that
Sorry, I
that
lost
particular
your
data
last point. You find the k equal to 6, then what?
Okay, now my voice is clear.
Hello?
Okay. Say for k equal to 6, and now I with this cluster
From
I
my side.
process some.
Hello. Am I
Hello.
audible? Yeah,
Yeah,
you are
you
audible
are
now.
very much audible. Yeah. Okay. Fine. So suppose I process this clustering method. My k is coming 6,
Yeah.
and
So
I
you're
did
saying that
the
you have found
further modeling and all. Yeah. So now when we do we are handling the unknown data for identifying the clusters. So it may so happen that one particular unknown data is equally likely processed to both the clusters. So in that case, is there any? Hello.
Yeah. Go on.
So is there any process to handle this kind of problem? This is question number one. And now question number two is, before doing this clustering, is there any feature transformation required for to make the clustering easy?
Okay, so the second question is a good point. Sometimes we try to normalize your features, right? Just to make sure that all comes in the same scale. And this is the demand of most of your ML models. You want your features to come into the same scale. Okay, but for now, you can skip this part. We will learn about this scaling and normalizing your features in MLP course in a better way. Okay, when to do scaling, in most of the cases you will find scaling is important part of
Sir,
your
MLP or MLT? You'll learn in MLP, you are saying.
In MLP you will find this scaling and all these things. Okay, so
Sir,
coming
how
to your
common
first,
is the cluster? Sir, in a practical world, how common is the clustering? Like in the PCA, we saw almost probably we use PCA for every data set. But is clustering used in every data set just like PCA, or it?
no. Clustering is different ML algorithm. It's not connected to any other models.
Yes.
Okay, so
It is not as common as PCA.
PCA is kind of pre-processing your data, where you just want to reduce your redundant features and you don't want to have them in your data set. So PCA is kind of pre-processing your data, cleaning your or represent your data set into better way. But the clustering is altogether different from PCA. It's kind of finding a different clusters in your data set.
Sir, so does it mean that first of all we should go for PCA and then we should go for clustering? Does it mean that?
No, it doesn't mean that. You
Sir,
can
we are
always go.
discussing objective function. Please complete it.
That's fine, sir. Please complete that part, but let us take other doubt also, right? Because these are questions are also relevant.
GP, you're right. In reality, that's how it happens.
It's not like that we are discussing something outside, you know.
Yeah, GP.
No, okay.
GP in reality. Sorry, just 1 second. GP in reality, that's what happens.
Okay, thank you, Vasu. Yeah, let him finish objective function. Then
Yeah.
So it depends the problem at hand. It's not universal that every time you do PCA and then
correct.
It's the problem at hand. Okay, so and you will be clear more about all this kind of problem when you will start doing start working on your data set. Okay, so different data set, different problem demands different algorithm. It's not kind of universal that you should go in sequence. You may find that you are doing, let's say, regression model you must be familiar with. So you are finding some relationship within the data set. Okay, so you may encounter data set where you first find different clusters and then do modeling about those clusters. So it's not like every time you find cluster and do modeling. So it's all depends upon your problem. Okay, so yeah, so coming to that objective function question, so isn't this objective function clear? So I was just explaining this. Let's say for this particular data set, this is your mu1, this is your mu2. What will be the objective function for each data point? You will find this distance, the distance of every data point from its own mean, and then sum over all those distances. That will become your objective function. Is it clear?
Just one part again. We will have two means, correct?
Yeah, two means.
So you will do it for mu1 and mu2 with each of the groups.
Each of the groups. So
okay.
These are your data
We
points.
must mu z1 square. That means distance of cluster mean to data point. This is clear.
Yeah, it is clear. So here, if you are confused within the data point, so JDI makes sure that you are taking the mean where xi belongs, the cluster where xi belongs, right? Because JDI tells the where the I data point belongs. So if JDI 5, it means that you are taking the mean of 5 cluster and where the xi belongs. Okay.
Okay, thank you. Thank you.
So just confirming, does minimization of the objective function ensure optimality?
Again, that depends upon your initialization and value of k as well.
Okay, and would an optimal cluster be the one which is the most compact?
Sorry. Yeah, that compactness. So if you think of this kind of data set, let's say this kind of data set. So what do you think will be the natural clusters in this case? What do you think will be the natural cluster in this case? So I probably assume this has a one cluster, this has a second cluster. This has a second cluster, this has a first cluster. I will assume
concentric circles, yes.
Yes, and right.
Sorry,
But
even I can take one cluster, sir, because the
sorry.
concentric. I can take one cluster itself, sir, to minimize my workload.
No. I my task is to find two clusters in this case. Okay. So my intention says that this will be my first cluster, this will be my second cluster, and probably this is the case, right? These are the same kind, these are of another kind. But if you apply k-means here, you will see that the objective function should give these clusters as a one cluster and this as a second cluster. This is my first cluster, this is my second cluster. So your problem actually, the optimal solution depends upon the data distribution, your k value, your initialization, and many other factors will be there to your that will affect your objective function. And the last one that you mentioned, that the minimization ensures that you want your clusters to be compact. Okay, so in this particular case, what we do, again, we apply kernel k-means. That is not again part of what you do. You just project into the data set where it becomes linearly separable or some kind of these things. So that is not covered in our lecture. So I'm skipping this thing. But there's different ways to handle all these problems. K values we have already seen how to choose best value of k, how to do better in initializations, right? Because all these affect your final clusters.
Sir, in PK, K is the number of cluster, na?
K is the number of clusters. It's a penalty function for k.
Sir, in this concentric circles, the mu k would be same, right? If I'm not wrong.
Mu k means what? Mu1 or mu2?
Yeah, mu1 and mu2.
So mu1 may somewhere lie here, mu2 somewhere lie here.
Yeah, I thought it would be at the center. Sorry.
No.
Sir, that question somebody asked before this, I forget who. Will it ever find optimal solution? I mean, the initialization. But I thought Prof said you can never find the optimal solution because it's NP hard.
NP hard because actually there are total possible. How many total possibilities there? K raised to power n total configuration possible, right?
N raised to power k raised to power.
K to the power.
K raised to power n. So checking within different values of k, different and possible out of those possible.
N raised to the power of k.
K raised to power n.
Yeah, it's.
You just check it out. Just it's k raised to power n.
It's just k for every data point.
Yeah, every data.
So n has k options. So one data point has k options, second has k, third has k. So n is k into k into k n times n power k.
K raised to power n. K into k n times k raised to power n.
Sorry. Okay. Okay. No problem. That doesn't matter. Yeah, go ahead, sir. You're telling me the logic.
So what I was talking? Yeah, that NP-hard problem. This NP-hard problem is just because if you keep on checking objective function values for each and every configuration, then it becomes very NP-hard problem. But most of the algorithm that if I talk about STLN, what it follows, it just takes different random initialization and it just pick the best one, the one which gives the minimum objective function value. Right?
Yeah, so correct. So that's why none of the existing algorithms will ever find the optimal solution. It's not guaranteed.
It's not guaranteed. Never guaranteed.
Yeah, that's
okay. So if you have solved your practice assignment or activity question, you may have found one question where you have been given this data set, right? And you have been asked what can be the clusters, right? So if you apply the k-means clustering here, you may end up with this cluster, right? And you may end up with this cluster. So what most algorithm follows, it keep on applying the clusters with different initialization and keep on applying the same algorithm and pick the one which gives the minimum objective function value. So in that case, if you apply the k-means algorithm using some tools like sklearn or keras for a toy data set, you may find that it will always give you these clusters because it's actually following some particular algorithm, and it algorithm keep on repeating and fix the minimum objective function value clusters. So it may end up always giving these clusters to you.
Sir?
Okay. Or these clusters rather than these clusters, because this actually gives you the minimum objective function value. There because it makes more compact in this case rather than this case.
Sir?
Yes.
Just a follow-up question on this topic itself. As Basu has rightly said, that professor has made a statement that this is NP hard problem, so we cannot get the optimum solution, right?
Yeah.
But at the same time, I don't remember exact on in which video he has also said that after several iteration you will reach at a at a particular point where not a single point wants to jump to nearby cluster, right?
So optimal. So that's
the ideal solution, or that's the optimum solution. So how come both the statements are correct, sir?
No, so you have got confused within convergence and optimal solution. Convergence doesn't imply the optimal solution. So convergence, when we call algorithm got converged, can you please mute yourself?
Yeah, just
yeah. So the convergence doesn't imply the optimal solution. Convergence means that if the reassignment of if there is no reassignment of any data points, then we call the algorithm has converged. Right?
But if algo has converged, it means I have found the ideal number of clusters, right?
It need not to be ideal solution. That's what we have discussed in that particular example, right? This particular example, or even if you take this this case, this circular concentric circle case, if you apply k-means here, you may end up C1, C2 here, and algorithm has been converged. But these are not your ideal. You're not optimal. These are not your optimal clusters or the cluster that you want.
Okay.
See the GP given an initialization,
yes,
some initialization, the algorithm will keep running till no more reassignment will happen, right?
Yes.
So the algorithm is converged.
Yes.
Now in reality, it will do this multiple times with any random initializations, which is called, as you know, it's called bootstrapping, right? So it keeps on doing it. Let's say it does it 100 times, then it will see which one of the 100 has given me the lowest objective function, and it will take that as the initial whatever centroid and give you the answer, right? But this doesn't mean that this is the best solution ever possible in all the options, because it depends on how the initialization has happened. That's all. So it may not be optimal, but given that you try so many times, it will be very close to the optimal in practice.
Sir, one question, sir. Hello, sir. Hello, sir. My question is, why always clustering based on the distance? Basically, in general sense, I thought that suppose in the float, in the paper there are some blue and red dots completely in mixed nature. And if I want to cluster blue dots and red dots separately, then how the distance only help?
Yeah. So
it depends on the
actually,
feature, not only
actually,
the distance.
yeah. So that is a good point. So this measure that here we have proposed Euclidean measure, you can define depending upon your problem and depending upon your nature of data set. Okay. So actually, what happens in our particular algorithm, ML algorithm, we tries to encode every features with some numbers, even though they are assembly balls or breadballs that you mentioned. When you feed those data points into your model, let's say your k, you have designed a k-means algorithm, right? where you feed your data points and that algorithm will give you the clusters. So that model, that black box demands the data points to be numerical one, right? So what you do, you just import those data points or do some pre-processing, then feed your data points. Okay, but your question is valid. If your metric could be different depending upon your problem, but that's how your ML algorithm works. You
Yeah. Sorry. Go ahead. Finish off.
Yeah, that's what I want to convey.
Yeah. No, sir, that is a very good question, actually. I was just wondering because, it's need not be a distance like we know distance, but it is some notion of distance because every optimization function is either L1 norm or L2 norm, right? So it is in some way it is a distance. Notionally, it's a distance measure only. Any algorithm.
Yeah,
Is that a
mostly.
correct statement? Because you're either doing L1 norm or L2 norm. There is nothing else.
Yeah, mostly we follow these distance measures.
Yeah, so that's what I was wondering. In fact, I mean, it's not strictly distance like we know coordinate geometry distance,
Yeah,
but
most.
some
Yeah.
some notion of distance.
Yes, some knows. Yeah. So again, this distance is a broader topic to discuss, and again, these distances are hyperparameters, and we never know which works better. But most of the cases, Euclidean distance are taken into account. Okay. So for till now we have seen three things. One, how to k means bugs, how to initialize better way, and that leads to k means plus plus. Then we have seen how to choose best value for k, and we have seen two methods. One elbow method, one add some penalty function in the objective function, and there is one popular method as well that I want you to check it out if you have free time. Just read about it. That's not hard to understand. It is called Silhout method. This is again a very popular method. That's why I'm mentioning here. You can go and read it out. It's not hard to understand. So, and it actually compares the clusters to the different cluster. I mean, if you have three clusters, then intra-cluster distance to the inter-cluster distance, and then check the compactness or say cohesive within the clusters and the separation from each of the clusters. So that is again a very good method, a good way to evaluate your clusters, right? So you can check it out later. So this is all about how to choose K. Then the next part is how those clusters look like actually. So if you see here, and here always we are taking Euclidean distance in different distance measures. This nature of clusters may be different, but here we are only concerned with the Euclidean distances. Okay. Now I'll do this for k equal to 2, and the same goes for higher values of k as well. Okay, so k equal to 2, it means that you have two means mu1, mu2, and these are your final cluster means. Now you have to find the regions which belongs to cluster 1 and the region which belongs to cluster 2. So I'm assuming the data set to be two dimensional data points, and your final mean, let's say mu1 is coming out to be here and mu2 is coming out to be here. This is your final means. Okay. So what do you think will be the regions corresponding to mu1 and corresponding to mu2? It's not hard to visualize here, right? You can say that each this part belongs to cluster 1 and this part belongs to cluster 2, because every data point if you choose here, it is at minimum distance from mu2 and you will assign it to the cluster 2, right? So you can easily verify that as well. This part belongs to cluster 1 and this part cluster 2. So this hyperplane actually dividing your clusters, right? So you can see that the middle line that crosses the line joining mu1 mu2 actually becomes your partitions of c1 and even you can verify it using this thing. You can call you have to, let's say some point x here, you have to assign into one of the cluster c1 and c2. So how you will assign? You will find the distance of that point from mu1 and mu2, and you will assign into the cluster 1 if it is this distance is lesser than this one, right? This is the way. If you solve these equations using x transpose x, I mean x minus mu1 transpose x minus mu1, is less than or equal to x minus mu2 transpose mu2 using just doing some algebra here, just manipulations of this term, you will get this equations. And what this equation says that this vector x vector is perpendicular to the line joining mu1 to mu2. So if this is your mu1 vector, this is your mu2 vector, so mu2 minus mu1 is your this vector, right? And your those data points where x1 goes to mu1, this is actually perpendicular to, so x1 transpose b is 0 means what? It's points which is perpendicular to b, and so b here is mu2 minus mu1. Here b mu is not 0, so it b, so it's some it's translated to some point to the origin, after the origin. So x1 transpose b equal to 0 will be somewhere here, right? Let's say if b is this, so x1 transpose b will be this. This will be x1 x transpose b equal to 0. Now what? X transpose b equal to c, some constant will be some this line. Okay, so here b is mu2 minus mu1, so all those data points which are perpendicular to this line, and in the middle of this line it actually becomes the partitions for c1 and c2. Okay, so this is the case where you have k equal to 2, and this equation says that this partition is nothing but the perpendicular line joining mu1 and mu2, and this says that this line actually is the middlemost point of mu1 and mu2, and this is very intuitive as well, right? And for the case of 3, let's assume you have 3 centers. So for you have k equal to 3, again 2-dimensional data set I am taking. Let's say you mu1 is coming out here, mu2 is here, and mu3 here. So what do you think will be cluster look like? The partitions will look like. So somewhere you can think somewhere here will be middlemost point, and this region goes to C1, this region goes to C2, this region goes to C3, right? Not hard to visualize. And so actually what is this? This is the line that intersect these lines. Okay, and this is the line which intersects this line, and this is the line. This is the line which intersects these lines, right? So these are the hyperplanes, which in 2D you can call it lines, but in the higher dimension this will become the hyperplanes, and we call those regions as the Borno region.
Sir, the area of the regions should be same, right?
The area of the region should be same. No, not at all, because let's assume let's mu1 here, mu1 here. Let's assume just here it is 0, here mu1 is here, and mu2 is here, right? So this become your mu area C1, this become your C2. So C1 area can be greater than C2. So it's not that area should be similar.
Professor has used the term perpendicular bisector.
Yeah, this is this line is a perpendicular bisector.
Yes.
And this is always a hyperplane, right? Because in 2-dimensional space it become a line, easy to visualize as well. But in higher dimension it become a, in 3-dimensional space it become a plane. In higher dimension it becomes hyperplane.
Sir,
Okay,
I think for the 2 point we can't say that it is bigger or not, because plane the graph could be infinite, right?
Yeah, that is a good point. Here you cannot compare the area, because these are very big numbers, and you know, because these are infinite, area will be infinite. But assume yeah, that is a good point. If you are even dividing your space into n number of space, those area for n number of space may be infinite, right? But because let's say you have assume this thing, you have 5 k equal to 5, and you mu5 is coming here, mu1 coming here, mu2 coming here, mu3 coming here, mu4 coming here. So area corresponding to mu5 may restrict to some finite area, and for mu1 it may be higher, and mu2 may be higher, mu3 may be higher, something like this, and the C5 may be lesser, right?
Yes.
So you cannot compare the areas. So it's not like areas always gonna be similar for all Borneo regions. Okay, so these are called Bernoulli regions. One more thing is pending in this thing is convergence. We always saying that the algorithm will converge, but we haven't proved that, and this algorithm will even converge or not, right? We have to prove this as well. So, do you want me to explain this, or you can read it out using lectures? Okay, I just give the ideas. You can go and check it out. If not, then you can go to the Saturday session where we can discuss in details. Okay, so convergence means that it means that after some number of iterations, your reassignment should stop. I mean, every data point should be happy with its own clusters, right? And this idea is actually comparing these two inequalities. So here, okay, so let me explain here these things. So what does mu zi t plus 1 mu t denotes? What zi t plus 1 denotes? And what zi t denotes?
Cluster in the tth iteration and t plus 1 iteration.
The clusters where the ith data points have in tth iteration, and the cluster where the ith data point is in the t plus 1 iteration, right? Right. And then what this will denote? The center of that cluster where the ith data points belongs in the tth iteration, right? And this is the cluster center or cluster mean where the ith data points belongs in t plus 1 iterations, right? So you can think if there are two centroid, let's call point xi here. This is your mu zi t, and this is your mu z I. This is your t, and this is for t. This is for t plus 1, and somewhere here you may have mu z I t plus 1 t plus 1, right? So it says that this is the current t is the current iteration, and t plus 1 is the next iteration where xi point will may be reassigned, and I'm assuming that xi data point is got reassigned, okay, to another cluster. Okay, so this is the cluster mean where xi data point belong in the tier iteration, and this is the mean where xi points wants to go, and this is the mean after the xi point has been reassigned. Then we again recalculate the mean. That is that mean. This mean. This is the mean before reassignment, and after the reassignment, mean will change, right? So this will become after the reassignment. So this denotes t plus 1. It means that after reassignment, after reassigning the xi data points to this cluster, this becomes your mean, and this is where the xi data point wants to go, but haven't gone, right? So this is that mean, and this is the mean where xi data points currently belongs to. All is these three notations clear?
Sir, the mu t zi t plus 1 is a little bit
What is
confusing.
V?
Sorry?
What is V? Xi minus V.
Okay, this I will come to later. I explaining these notations. These three notations should be clear. Otherwise, this derivation will go blank.
Sir, can you
How many more slides you are going to explain? Because I have BDM session from 8 to 9.
Okay, so 3 more slides. This is the last proof that I want to explain.
Can you repeat the earlier part a little bit once again, please? The convention.
Yes. So
I mail you with your permission, sir.
I think we can have these sessions tomorrow, sir. Tomorrow we have a session, sir, right? Saturday?
Yeah, tomorrow, Saturday, 6 to 8 p.m. session.
Yes, I think we can start from
Okay,
here.
so that
Most of the people have
okay,
other
so,
spaces like
sir, it would
PDS
be
and
great.
Okay,
sir,
so
one operational question, sir.
And this is a very
just out of
important
curiosity, sir, why are
okay,
we?
so okay, please give me 1 second. Okay, so it's getting hanged.
If you please explain the next slides in the Saturday, because I have
okay,
BDM.
so I stop it here. I will explain this convergence part in the next session,
Yes,
And
sir.
so
Static
anyone who
process
wants
notations
to
and all. So.
drop up can drop up, and if you're very rushed, please stay. Yeah, so someone was
Sir, quick
asking me
question.
some
Sir.
operational
Yeah.
queries.
Yeah. Well, operational question, sir. Sir, why are we ahead in terms of doing all these sessions by almost 1 week? Sir, I understand that it's probably aligned with the release of the content, but if you see the exams are, the deadline for this week is only week second. The deadline for this week is next week, right? Next weekend. But we are already covering week 4, so we are running ahead of time. I mean, I have no problem, but we just
No, actually deadline was extended. I'm not sure why the deadline is like that, but generally we give deadlines for 10 days, and ideally big 3 deadline should be this Sunday itself. But I don't know why it's in the coming week. You must have seen in the previous term as well. We have a session just
No,
before the deadline.
It was extended because there was some delay at the beginning of the course because the website was
Delay because delay within 2 or 3 days, not for 1 week.
Website. Yeah, so this is some sort of support to students. I'm not saying I'm not complaining about it. This is some sort of support to students which have been extended by institutes, sir.
Yeah. So these all life session is already decided.
So
That's why we are keeping at the same date.
We are going to have sessions on
And
Friday
it's
and
not
Saturday, right? Because earlier we used to have a Thursday and Saturday, right?
Yeah, but still it is decided on Thursday. I'm not sure how